Swayam Prabha. Digital India. Educated India.
Now, we look at the linear wave theory assumption. Quite a few assumptions. The first one, the fluid is incompressible. So, not like the air that can be compressed, right? But here, the fluid is incompressible. That's the first one. And the density is a constant. So, which means we don't looking into the density change. So that's a constant density as well. That's the first one. And gravity is the only restoring force we consider. We ignore the surface tension. We ignore what else? Coriolis force effect. So when you are coming to very small, like wavelengths, because the Coriolis force is a much larger wavelength, the dimension. So that one, you are able to ignore that one as well. And also, the pressure at the free surface is uniform and constant. The pressure at the free surface is the same. Not like if there is a storm coming, sometimes the pressure system, you will see the low pressure or high pressure variation along the surface. Then that will affect the waves as well. So we ignore all of that. And another thing is also the particular waves being considered does not interact with another water wave. So there's no wave and wave interactions. So that's another one. So you can see everything is ideal. And the fluid is irrotational. And also the waves are plane or a long crested. So that's two-dimensional waves. Okay? And the wave amplitude is small compared to the water depth. So although we only say small amplitude, that's the last assumption, but it also have quite a few assumptions before that. Okay. So this is a linear wave theory or assumptions we are looking into. And when we are talking about these waves, we also have the definition of the velocity potential. So we introduce the movement of water particles under waves is dictated by the distribution of the velocity potential. And when we are doing that, we are able to see, okay, if we have the velocity potential is a gradient along x direction is u. And the potential along z direction, that's a vertical column, that will be w. So that's a definition of the particle velocity, so the water movement of that. And also the negative, what is a negative sign over there, indicate that particle motion is directed towards the region of the lower potential. Okay, so towards the lower potential. You know that water flowing from the higher potential to the lower potential. Or we say the down gradient. So that's a definition of the particle velocity. And then the velocity potential we are able to write in this format. So the first, of course, gravity, frequency, wave height, and that will be the amplitude. And we also have another term over here. So this term, which is a variation with the water depth and the elevation. So that will be affect all of that. And then the last term is periodic variation, the sinusoidal functions. Same thing, similar to the cosine. So which means this potential and the elevation, surface elevation, they have a phase difference. They have a phase difference. So because the other one we use a cosine, kx minus omega t. So here we use a sine. So that there is, you can still using the cosine, but you just add a phase on it. So that's a potential. So based on all of that, we are able to get a dispersion relation, so which is wavelength and speed. So for the wave celerity, that's the speed of the wave transformed, like transported speed of that. So how quick the waves moves. So that will be what we are having is a celerity. So that's a length divided by the period. And what is a dispersion relation? That's describe how the speed of the waves of different lengths and period varies. So this is a relationship. So wavelength, period, and then we have the tangent h. So the tangent h is a hyperbolic tangent function. So are you able to solve this equation? We won't be able to find the solution, exactly the solution. It's very hard. But if you are using the find zero, you may be able to get the solution, numerically, or use an iterative way to find. You first guess the solution, right? Then you substitute that too, and then there is an error. Then you, just do that until the error is very, very small. In engineering, we use that quite a lot. You are also able to use, what programming language you are using? MATLAB. MATLAB, yeah. That's very good. So you all use the MATLAB. We also use the MATLAB. So there is a find zero function, F0, a lot of similar techniques you are able to, So we use that to solve it. So what's the first guess you have? Normally we use a deep water wavelength because that's only, deep water only depends on the period. So we use that as a first guess, then substitute in one by one. So that's, we use quite a lot. And have you used Python? Yes. Do you use Python? So you use a MATLAB. So your laptop, you all have a MATLAB? Yeah. Okay. Yeah, that's what I'm thinking. If you have the MATLAB installed in your laptop, so maybe Wednesday you can bring your laptop. I can send you some code. Then we do some simple modeling. Because first I was thinking to you, I have both Python and MATLAB. Because Python now is the reason we moved to Python is Python is free.
Python?
Python,
Is this Python or Jupyter?
Jupyter or
Yes,
Python?
I use Anaconda, but it's a similar. Doesn't matter. That's whatever you are using. So either way, whichever you feel more comfortable, we can use that one. I have both code. So then that's good. So we do a little bit like modeling part. So if you're using MATLAB or Python, easily you are able to solve this type of equations. So we are doing that because you are not able to directly solve this one. So it mentioned the method you are able to solve that is iterations. And then we are also looking at the next one, the approximation. We also use that quite often. So you can also use this approximation to solve it. Okay, so that's using the algebra approximation, we are able to solve that as well. And also the error is very small. If you're using that iterative method and also compare with approximation, you are able to see very, very small. So it's in engineering perspective, that's acceptable. So now we come to the first example. A wave with period of 10 seconds propagated towards the coast over a uniformly sloping shelf from a depth, which is a 200 meter, to a depth of 3 meters. Find the wavelength and the celerity at these two depths, assuming linear wave theory is applicable. Do we need to go through, or you are able to do it? It's okay, right? Yeah. So for that one, yeah, that's just to use those equation which has been given. You are able to see, first is in the deep water, 200 meter, and then propagated to 3 meters. Then you are able to solve that based on the given conditions. Is that okay? We keep going? Okay. Yeah. If not, then you can ask me later. So this is a tutorial question. You can also do that. It's similar, just to give you a different range of this. But I also would like to mention is, if you use a program, then you are able to do a small program, then that will be very easy. Next time, you just change the given condition, then you can get all the solutions. Yeah. And also, there is another interesting thing is, because we are using because of the dispersion relationship, there is a tangent edge, the hyperbolic tangent function over there. So you are able to use that. What is a hyperbolic function look like? When in this area, when the kh is very, very small, that's like a linear function over here. But when it's approaching very large, the kh, then that is a 1. So then if I'm using this equation, this relationship, then you are able to estimate the wavelengths, right? So when this is a very, very small, close to this area, and then when you go into like a 1, then this term, that's a deep water. So we will see, okay, what do we mean over here? First thing is for shallow water. That's for shallow water in the first part over here. And this is like a linear. Tangent kh, that's approximated to the kh. So then you don't have the wavelength inside the function anymore. So you are able to get this relationship. Then you are able to see the celerity actually is gh square root. That's a shallow water waves propagation velocity. Quite a lot. If you look at if there is a tidal wave at the river mouth, if the tidal wave, not a wind wave, okay, I'm not saying tidal wave at the river mouth, it will be propagated along the river going up. Of course, if the slope is very small, and then also the water depth is not very deep, you can always get how fast it will be propagated is a root square gh. We use that quite a lot to do the estimation of the tidal wave propagated upstreams, because that will be affecting the what's the saltwater intrusion. We will see how quick and how far those saltwater intrusion will be going in the river side. So that's one thing, okay, for the shallow water. And then if you look at the deep water, that's on the other end of the circle. That's when tangent KH is always equal to 1. Then that's this equation over here. So the wavelength will be the GT squared over 2 pi. That's the deep water waves. So that's what you are able to see. You are also able to use that. 2 extremes. If you know it's a shallow water, quickly you will know what is the celerity. Same thing, if you know that's a deep water, then you will also be able to estimate. You don't need to solve that equation. Yeah. But only in between of that, then you need to solve that equations. So that's very common in engineering application. We use these techniques to do the analysis. So that's deep water waves. So that's basically is a summary of what we are having over here. Okay, so that's also the when is a shallow, when is a deeper. You can use both the KH relationship and also the H over L, the depth and the wavelength ratio as well. So that's what we are able to get the summary. Okay, so that's tutorial question. Actually, is also based on what we are looking at there. So we quickly look at this one. A small amplitude wave is traveling in a water depth, to 20 meters. Compute the wavelength and the celerity for the following wave period. T equal to 5 seconds, 15 seconds, and 50 seconds. So, and also classify each of the above waves as being either deep, shallow, or transitional. So are you able to solve it?
Yes.
Yes. That's no problem, right? So how many of you are going to have a assessment, the exams? Okay. Yeah. So then you just make sure you practice by yourself. The different examples, yeah. So here is just a solution, but you are able to do that and then make a comparison as is. Okay, we continue the lecture. So now we are talking about kinematic, which is particle motions. So we mentioned the particle velocity before by using the velocity potential. So you defined the U and the W. And here, again, we are using the particle motion and to define it. And the particle motion, those particle velocity actually also very important when you are coming to the sediment mobilities. And also, you come into the wave forces acting on the structure. So a lot of time when you design all of the structure, you also want to know what the force, the wave force acted on the structure. So that's we are using the particle velocity to the one of the key parameters for the calculations. So we are introducing this one. I like this diagram. Actually, this one shows very clearly actually the wave propagation, which is not the particle moving, transported, is the energy. You see, if you look at the yellow one, you are able to see. Is it just along this orbital over here? is moving over here. And this one is moving here. And of course, if you're following this one, this is moving very, very small. And if you keep going down to the bottom, almost not moving anymore. Yeah. So very clearly shows it's not particle transported, okay, but it's energy. And when you are looking at this one, so maybe we will see. We will together to look at what direction is a particle motion under the wave crest. Under the wave crest. So it's the same as the wave propagation direction, right? But if you're looking at the particle motion under the wave trough, this is a trough. That's opposite to the wave propagation. So if you're looking at that. And also the direction is a particle motion when the free surface, what is direction is a particle motion when the free surface passing through z equal to 0. I heard some 0. Passing through the 0 equal to just the mean water level. Downward. Mm-hmm. So if we look at that one, the particle motion when it's passing through the z line. So we have to say horizontal is 0. Vertical. So we have to separate the two to saying that. And what the shape are the particle passes? Circle, or we say orbital. Yeah. Yeah. Elliptical will be more accurate because circle is a special type of the elliptical. And what happened to the particle path close to the seabed?
Is this a deep water?
Deep water or shallow water?
Okay, if it's a deep water,
It is
almost not moving. Yeah,
not moving.
yeah, very small, maybe. Yeah, and if in the shallow water, just just like a line. Mm-hmm. Yeah. Yeah. So that's a orbital motion. So we are able to use this equation over here. Actually, try to analyze what just now we discussed. So that's u velocity. Then of course you are able to analyze that. This is the same as eta. So the phase is the same as the eta. And then you have the vertical. Then you can see that is a derivative of eta over t. So there is a phase difference, 90 degree, the phase difference from the surface elevation. So that's what we are having over here. Then here we introduce another thing, is a velocity amplitude. That's this part. We have the first part plus the cosh and the sinh. They are ratio between that. So we are having all of this and also the vertical one as well. So when you are having this, you are able to see when you have the elliptical shape. So because of this, you are able to see because that's the amplitude. That's the amplitude. So one is a vertical amplitude, another one is a horizontal amplitude. So then, which determines the shape of the optical shape. So that's what we just discussed, right? So like in the shallow water, what it look like, and also in the deep water, what it look like. So that's what we are having. So that's all. Now we look at the kinematic. Consider a wave with a period of this 8 seconds, and the height is 2.5 meter, traveling in a water depth is 15 meter. Estimate the horizontal and the vertical velocity amplitude at an elevation of z equal to -5 meter. So you are able to do the analysis. Yeah, that's just from the equation from last slides, right? So you are able to use all of this then to do the calculation. Just substitute all those variables in. Then you are able to find the amplitude of horizontal and vertical. Yeah. So that's an example. And also there are some solutions over here as well. Similar tutorial question as well. So you are able to do the similar type of the calculations. Then I'm coming to talk about another thing, is a pressure distribution. So we all know in the presence of a wave, the subsurface pressure distributed is given by the sum of the static and the dynamic pressure. So here, this is a static. That's just a rho g h, right? And now we have the dynamic, the waves coming on the top. So we will have the pressure that is you add on the dynamic part. When it comes to deeper and deeper, that dynamic pressure will be smaller and smaller. Yeah. So you have the largest one at the top. So this is a two things. Another situation is this one is under the location is a trough, right? So then, of course, that pressure, dynamic pressure, you have to take away that one because it's under the mean water level. So that's how you calculate this one. But when you write to the formulas, so this is a hydrostatic pressure you add on, and then the next part you are having is dynamic pressure. You add all this together, you get the total pressure. But how can we use this one for? I remember there are some like monitoring study people are doing, and also Professor Raj mentioned about the monitoring as well for different sensor. So to measure the surface elevation is not that straightforward. So a lot of time we use a pressure sensor. We measure the pressure at a certain depth. Then we use our equation to calculate what is a surface elevation. So that's one of the techniques. Okay, so to measure the waves. So for this equation over here, if you know the pressure, then you just rearrange. You get the surface elevation. So now you look at this example. An average maximum pressure is given is 124 kilonewton per meter square. measured by a subsurface pressure gauge in seawater. And also, you know, the density is 1,035 kilogram per cubic meter at an elevation of 0.6 meter above the bed in a water depth of 12 meter. The average frequency is given is 0.0666 hertz. Now, ask you estimate the wave height, assuming that linear wave theory applies, and that the average frequency corresponding to the average amplitude. So you see, there are assumptions. Average, so they're also corresponding to that. Because in the real environment, you know that it's varying, right? So the frequency and also the pressure, you won't get a like constant value. So, but we are using the average maximum. So you will do a certain length of time of the measurement, then you do the average, then you assume that will be the corresponding frequency and also the pressure maximum as well. So you do that. Now you're able to do this.
Pmax is equal to Ps plus Pd.
Yeah.
Static plus dynamic.
Yes.
And substituting these variables, and we get the eta. In H, we can get the name.
Yes, that's correct. So yes, you are able to use these techniques to do the measurements.
So here eta will be the H weight.
Sorry?
With the eta, the free surface elevation will be.
You have 2 times to 2, yeah. Because H is 2 times of eta. Yeah. Okay, so that's another application we are having. So pressure. So for the tutorial question, it will be similar. So given a wave height is 3 meter with a period of 12 seconds, propagating in a water depth is 16 meter. Taking the density of seawater again is 1,035 kilogram per meter. So considering a bottom-mounted pressure sensor, what would the maximum total pressure be? What would the amplitude of the pressure fluctuation be? So it's similar. A little bit different. So here, the sensor is at the bottom. What is the maximum total pressure? So that will be the PS plus PD. Hydrostatic and the dynamic. And then you also want to know what is the amplitude of the pressure fluctuation be. That will be the amplitude of the dynamic pressure. So just to make sure all those definitions are clear, then you are able to use all those formulas to do the calculation. Yeah. So by using this equation over here, because you know the eta is a half h, yeah. Then you are able to find out the p, and then also you are able to find out this part. So just one more step to find out this one. So we don't need to go through the solution, right? Okay. Then we come to the next one is the energy and energy flux. So basically today we reviewed all those like linear wave series. So wave motion represent mechanical energy because that's all mechanical force we mentioned before is either wind or is an earthquake or some mechanical force. Even like if you throw a stone in the water. And also, what two energies we are having over here? One is a potential and one is a kinetic. Okay, so potential energy and the kinetic energy. Potential energy that's generated due to the wave height. And the kinetic that's due to the velocity. So the definition, the energy density is a wave energy per unit area of seabed. Okay, so per unit area of a seabed. And the energy flux, or we say that the wave power is the same, is the rate at which energy is transported. So because we know the waves transport the energy, right? So that will be the rate of that transport the energy. So that will be the energy flux. When we come to the total energy density unit square, so it's evenly distributed between the potential energy and the kinetic energy. So they both is 1/16 of rho gh square. So that's related to the wave height. So that's what we are able to have. So it's half and half for each. So the total wave energy density will be 1/8 of rho gh square. So that's a wave energy. So you are able clearly to see the wave height determined the wave energy pretty much. And the energy flux, that will be, this is the magnitude of this. And that's the speed of energy propagation. What is this? If you remember the wave theory we had, this is a group velocity. Yeah, so yeah, that's a group velocity. We base on this, all of that. That will be the energy flux. So energy flux is E times the CG. Yeah, so that's a group velocity. So how quickly the energy be transported. So that's energy we are having. Again, this diagram helps us to understand the group velocity and just the normal velocity of the. So that's the slowest one you are able to see, and this is the fastest one, and then the superposition together, then you get what's the velocity to look like. So that's a group velocity, the last one, the blue lines, that's a group velocity we are looking into. But are they same or they are different? So if you look at the diagram over here, wave group velocity is the speed of group waves. If we follow the dot below, you are able to see the green one and also the red one. So they are different velocities. Their values are different. So again, we are using the formula to help us to understand. In deep water, the group velocity, if you are going to the singe, so that's infinity. So this part that goes to 0. So in deep water, the group velocity is a half of the deep water velocity. Yeah. And if you go to shallow water, so you are able to see this one, the CG, group velocity in shallow, that's root GH. So that's a same. So when in shallow water. Then, of course, in between, in the transition zone, you have to calculate. That will be within the range. Okay. And this diagram actually shows annual mean wave power, the global. But this is a very old diagram. That's a 2008. Actually, the people have done the calculation or analysis of wave conditions where you have the largest waves. And then if you are looking into utilize the wave energy, where you think you will using the wave converter or generator. So actually for us in Australia, we did look at this area. Because when we are coming to the Queensland area, our wave condition actually is not that great for generate consistent waves over there. So, but underneath you have larger waves. So from here you are able to see that's between 40 to 60 latitude, no matter it's the south or north. So that's what we are looking into, the annual wave powers. So today, we also have another example over here. It's the estimated wave energy flux of a 1 meter high, 10-second period, wave propagating in a water depth 30 meter. The water density is 1,026 kilogram per cubic meter. Now, estimate the wave energy flux. First, calculate the energy density. Then calculate the CG, group velocity. Then you are able to find what is the energy flux. Yeah. So we have the answers for each step. Then you just use a formula for the calculation. Then we look at another tutorial question. Estimate the wave energy flux of 1 meter high, 10 seconds period, propagating in a depth 5 meter, and compare with the answer from last one. But last one is 30 meters. The wave density is same. So if you compare, what's the difference between these two? L0 is the same. Energy density is the same because they have the same wave height, right? And what is different? Wavelength. Wavelength is different. So the wave number is different. Then if you look at the celerity, different depths, right? And then group velocity definitely is different. So the energy flux in the tutorial question in the shallow water, the 5 meter one is 8,091. But in the deep water, yeah, so we have, yeah, is a larger. So this one is a 30 meters one. Then which one? This one is a larger energy flux compared to the shallow water energy flux. Actually, they have the same wave height, but because of different water depths, yeah. So the propagation rate is different. So the energy flux is different. Okay, so that's a coastal process from the linear wave theory. So I will stop here for today, and tomorrow we are looking into the natural wind waves. Yeah, thank you very much.